Hi, everybody. This will be the lecture on using the instrumental variable approach, especially when we do the two-stage least squared estimation. Credit to Mike Bailey, whose lecture slides I drew from, and whose textbook I'm also drawing from. So let's start with an example. And this is a study that Levitt did, trying to estimate the impact of increasing police on crime. And so clearly in this situation, we might have a problem where police is an endogenous variable in this context, in the sense that it's actually correlated with the error term. And so this could be because of omitted variable bias, because there are some factors that influence both the number of the police and crime rate, such as maybe drugs or level of poverty in the city. We could also have some kind of simultaneity bias here, where the crime increases police and police decreases crime. For those who are interested, the textbook does go into how to deal with simultaneity bias, although that will not be evaluated for the exam. Right, so in all these cases, we have a situation where there's a kind of positive correlation between the error term and the variable, which means this is now endogenous. And now the key thing about an instrumental variable is that there might be some variation in policing that's not caused by a omitted variable like poverty, and it's not caused by simultaneity bias from more crime, that is actually exogenous. And we want to capture that exogenous element, and looking at the relationship between the exogenous variation in police and crime using the instrumental variable approach. And just so visually, this is how you can think about when the variable is exogenous, it does not have any relationship with the error term, or whether it is endogenous, where there is some kind of relationship, correlation with the error term. For example, we might have an omitted variable called this A, which is correlated with both the endogenous variable and the outcome of interest. And even though the endogenous variable has a direct impact, if you don't control for the omitted variable, it captures both the direct impact and the indirect impact through the omitted variable. Right, and so the logic of the instrumental variables is to try and isolate the variation in the endogenous variable. Here it's the number of police that is actually exogenous. And then we take this remaining exogenous variation in the number of police and estimate the impact of that on crime. And the idea is that there could be some factors that also contribute to the overall increase in number of government employees. Maybe there's employ more people in election year or budget surplus, and that's completely unrelated to the crime rate. And so this is these factors that cause increase in the number of police is actually exogenous. And so this study by Levitt actually used the number of firefighters as an instrument. The idea is that there's some kind of positive correlation between the number of firefighters and the number of police, in particular, relationship between increases in the number of firefighters and increases in the number of police. But this is completely unrelated to the actual error term in the crime equation. Right, and so this is actually what they did is when they just did the OLS estimate, they do find that, sure, having more police in the previous year leads to higher crime this year, and clearly there's some omitted variable bias. When they throw in city fix effects, just controlling for every single city, there's a small negative relationship. But using this two-stage least squares approach led to a very large negative relationship, meaning more police actually do reduce crime.
So what exactly is the two-stage least squares approach? Well, unsurprisingly, this approach has two stages. So as a starting point, this is a model that we want to estimate, where X1 is the endogenous policy variable of interest, for example, the number of police, and x2 is just some other additional control variable that we want to add in our model. So what we do is, in the first stage, is we run another regression where our independent variable now is actually the endogenous variable itself. So we regress endogenous variable on the instrument, as well as this additional control variable. So the control variable just has to be included as well. And then what we do is we actually take the predicted value of x1 given this first stage regression. So basically, what is our best guess, our best estimate of what x1 is, given what we observe in our instrument and our additional control variable? Then we replace our endogenous variable with this kind of restricted, reduced version of the endogenous variable, which is this predicted value of our endogenous variable, given what we observe in this plausibly exogenous instrument. And that is the regression that we run. Stata would do this automatically for us, and we need Stata to help us calculate the standard errors, because the standard errors from the second stage is incorrect if we just plug in this predicted value, because we do not consider the fact that there's uncertainty as well in the estimation of x1 that needs to be accounted for. So visually, this is what's going on, and I like showing these figures. They're called also called DAGs, directed acyclical graphs, that show all the potential causal relationships. And I like to think about our endogenous variable having some source of endogenous and exogenous variation. And the endogenous variation is indicated by the red arrows here. So there's some kind of emitted variable bias, some factor A, like say the poverty rate, that is explaining both the endogenous variable, our number of police, and our exogenous variable, the crime rate. But there's some other variable that we can find that explains, that causes some variation in x1 that is completely unrelated to this emitted variable. And so what we actually do is, when we do this first stage regression, we get this predicted value of x1, we kind of extract out, pass out all of this endogenous variation, throw it away. We have what's remaining is this kind of reduced version of x1 that is only the x1 that is caused by z, or due to a variation in z. And that is the variable that we look at, that is now exogenous, because we've passed out all of this endogenous variation. And so there are two conditions that need to hold for a valid instrument. So when we talk about conditions for a valid instrument, we're talking about our identification assumptions, our assumptions to have a kind of credible causal estimate of our program and policy of interest. And so the first one is that there should be a non-zero correlation between our instrument and our endogenous variable. So we can think about it, Bailey talks about this as the inclusion condition. Baldrige refers to this as instrument relevance, and Angrist and Prishka talk to this about it being a strong first stage. It's a strong first stage because it's the first stage regression where we need there to be a lot of the variation in X is actually explained by the variation in Z. There's actually a high R squared in that regression. We'll get back to how we test that in a minute. And then the second one, and this is the one that is impossible to measure, unfortunately, and impossible to test for, is that we need that the instrument itself is exogenous. And so technically, it's that the covariance between Z and the error term in our main estimating equation, in this main estimating equation that we use when using this predicted value, that the correlation between the instrument and this error term is zero. And so this is really just requiring that it's exogenous in the sense of the relationship we want to estimate. Bailey calls this the exclusion restriction, but there are really two elements to it, and different textbooks refer to this differently. I'm going to be using the definitions of the Woolridge textbook, but the two components, one is what often people call the exclusion restriction, and the idea is that Z, our endogenous variable, cannot directly influence Y. It can't have its own cause on Y. It can only have an impact on Y through the endogenous variable. The second restriction here is the conditional independence assumption, which is basically saying that this new instrument should be as good as random, basically. And in a very specific case, that there should be no other omitted variable biases, maybe creating a spurious positive correlation between this instrument and the outcome, and it really should be kind of causing the exogenous cause of variation in X1, which then again is related to variation in Y. Right, so two conditions underlying this fact that you need an exogenous instrument. A needs to be, or B needs to be as good as random, and A, it can only impact the outcome through this endogenous variable, because it's really the impact of this endogenous variable that we care about. There's the third condition, which is called monotonicity. And we'll get at it a little bit in more detail when we talk about the application of instruments with randomized control trials. But the idea here basically is that the effect of the instrument on the endogenous variable always goes in the same direction for everyone in the population. So in the example we used, the relationship between when number of firefighters is an instrument for policemen, there's some kind of positive relationship between number of firefighters and policemen. But we need that positive relationship to hold with everybody, all the cities in the sample, even for those cities that we do not observe this, because maybe there might just not have been that variation that's picked up in that city. We can't have a situation where actually in some cities the increase in firefighters would actually lead to a reduction in number of police. Again, impossible to actually test for this, but a very important underlying condition for the instrumental variable approach to work. And so again, I think visually it's really nice to try and understand it by looking at these figures. The most important thing, kind of a takeaway I want us to have from this lecture is that it's actually really hard to find a good instrument in a study, and there's actually a kind of being a reckoning in the discipline over the last couple of decades that like instrumental variables has fallen out of favor immensely, just because of these problems of we can't really ever know if it's really a good exogenous instrument. And so one example, right, of these two conditions, well, the two conditions for it being exogenous is, here's an example of the exclusion restriction itself, or the being violated. And this would be the case if the instrument has a direct impact on Y itself. This would be if the number of firefighters for some reason are able to directly reduce crime. And so we're picking up this estimate with this new two-stage least squares framework, but it's really nothing to do with the police. It's just because the firefighters themselves are directly causing a reduction in crime. Who knows? People are just scared to go out and commit crime because these big burly policemen are running all over the place chasing cats in trees. All the noise is just scaring people that think it might be policemen when they hear the sirens. Right. We can't test for that, but we have to assume that, and we have to be able to tell a compelling story why we think in our case this instrument does not have a direct impact. And then we might have exactly the same emitted variable bias that we had with our original variable x1 with our new instrument. There could be some kind of other emitted variable that's kind of positive correlated with both our instrument and with the Y itself. I mean, for example, we could have a situation where we have economic booms. This is now C is just like, good times, and good times leads to more firemen, and good times leads to also more policemen, and it leads to a reduction in crime, totally unrelated at all with, and so this positive relationship we pick up is really due to the good times of economic conditions and nothing to do with the actual number of policemen.
It's an assumption we need to make. So what we can do for instrument relevance, the first condition, is that we can just test if there is what they call a strong first stage, is that there's just a strong relationship between an instrument and the endogenous variable. We can use that same equation for the first stage and just see what the value of the t-statistic is. Historically, people wanted to have a t-statistic at least magnitude of 3 or higher, but increasingly people are saying even that the threshold should be much higher than that. And as I said, there's no test for whether the instrument itself is endogenous. We cannot test for the exclusion, restriction, or independence. Right, so let's go through a case study together. And so another example we have here is the impact of new natal intensive care units on infant mortality, also called NICU. And so those are the kind of containers where incubators that babies are put in when they've had premature births or there are some complications. And now you might want to estimate this equation where mortality, infant mortality is on the left-hand side, and where the baby went to an NICU is on the right-hand side. And clearly here there's a massive selection bias, which is captured through the admitted variable bias, is that the most complicated births and most severe health challenges leads to baby being sent to the NICU, which could also lead, the same factors are related to mortality. And in fact, there is this positive correlation where mortality rates are much higher for babies who utilize the NICU compared to those who do not. And so what we can do is we can use distance to the NICU as an instrument. So basically, the first condition and the near NICU is a kind of binary variable equal to 1 if somebody lives close to it. And so here we see that this is the first stage regression, where the left-hand side variable now is actually whether somebody is using the NICU, and the right-hand, the instrument here is whether somebody is close to it or not. And sure enough, people who live closer to hospitals that have an NICU unit are more likely to use it. And you can say that this is actually a valid instrument, at least in terms of the first condition, because the t value is extremely high, 178. It is highly, highly significant. Now, the question or the more challenge is this instrument actually exogenous? And so we can think of a admitted variable bias here. There could be a situation where, like, these NICU units, of course, are only in hospitals that are large, and these hospitals might only be in densely populated urban areas, and maybe you only have poor families who live in the kind of inner city, and these poor families are more likely to suffer from birth complications. So a classic admitted variable bias. But, and here's the tricky thing, which is genius and a little bit tricky to think about, is even though our instrument might not be exogenous because it might be correlated with some kind of with poor families, we can control for that. We can control for the poverty where somebody comes from. And so the instrument would be independent, conditional on poverty. After controlling for poverty, it is in fact independent. And so the first stage would also include this variable, which is basically the poverty status of the community where somebody comes from. And then the second stage, very importantly, includes the same control variable that was included in the first stage. And let me just show this again visually, where we have this endogenous variable where the baby is sent to the NICU unit. And there is clear selection bias here because complicated births leads to both higher mortality and higher usage. And so we want to use an instrument which is which does not suffer from this endogeneity and which is correlated with usage, and this is distance. But there might be another source of endogeneity for this variable because it might be correlated with poverty, which in itself is correlated with the number of deaths. But if we control for poverty in the first stage, we're effectively switching off this source of endogeneity. And this is exactly what they do. And so the second column here is what happens to the naive OLS regression if you just add in a bunch of additional controls, and it goes from being a positive relationship to a negative relationship. So that's a good thing. This suggests that there was a lot of omitted variable bias at play here. But the two-stage least squared estimate is the magnitude of this negative relationship is much larger. It's in fact almost 40% larger. So the multivariate OLS was likely kind of biased towards zero and was underestimating the true positive impact of using NICUs on mortality. Right, so as a final part of this lecture, there are a couple of extensions that are important for you to know about. The one is multiple instruments, and the other one is some other shortcomings of the instrumental variable approach. And so with multiple instruments, the idea just is that you don't need to only use one exogenous variable. You can actually use multiple different ones if you can find them. And then that just means that in the first stage, you throw in all these different variables, and all of them separately can actually predict the endogenous variable, which is included in the second stage, in addition to this exogenous control variable. So all these instruments would then be included in the first stage, but not the second stage. The test for a strong first stage is slightly different. Now you just don't want to know if one of these relationships is significant. You want to know if all of them contribute jointly to explaining a lot of variation in the endogenous variable. You do this by doing the F-test, by saying they are jointly equal to zero, all three of these coefficients, meaning that none of them have any impact. So that's an F-test because it's actually a combination of variables you look at. And historically, people have said you need an F-test value of at least 10. And so with one variable, an F-test of 10 would be t-statistics of the square root of 10, which is 3. But now people are saying that is actually way too small because of all the other challenges that I get to in a moment. You need a much larger F-statistic. And so one of the kind of, let's call it more insidious, nefarious challenges of the instrumental variable approach is that the cure can be worse than the disease, especially if the instrument is weak. And with weak, I mean that there's a very small correlation between the instrument and the endogenous variable, meaning that that first stage is not very strong. And now let's say there's an instrument that is just slightly endogenous. It's not a perfectly independent. There's some small correlation between the instrument and the error term of the second stage. The problem is that this small potential bias gets inflated and expanded if there's a very low correlation between the endogenous variable and the instrument. So you can create a much larger bias if you have a very weak first stage. And so here are two equations that you don't need to memorize. I have a mathematical appendix to say how it's calculated, but it just helps you to understand how these two biases could operate. And so when you have an OLS estimate, the bias is related to the correlation between the error term and endogenous variable, which by definition is endogenous because it's positive, and also a function of the relative standard deviations. Here, in the second estimate of the two-stage least squared estimate, it is now the bias as a function of the correlation between the instrument and the same error term. So that is, if this correlation is much weaker than this correlation up here, that should be good news. We have at least less of a bias because it's less endogenous. But you divide this also by the correlation between the instrument and the endogenous variable. And so if this correlation is very small, if you divide by, say, 0.2, you times the whole bias by 5. So a very small correlation expands it immensely. And there's an even more challenging problem with instruments. And this is something where it's a bit more technical. You guys don't have to understand it perfectly because I don't understand it perfectly. Is that a two-stage least squared estimate is what they would call, it's consistent, but it's actually biased. And so there's a distinction in statistics between consistency and bias. And what this basically means is that the expected value of our estimate is actually not the true estimate, but it converges to it as the sample size increases. And this is why we talk about the probability limit, is that you can't talk about the expected value, but you can talk about the probability limit. Probability that it is actually the true estimate gets higher and higher as the sample size increases. But that means that you could have bias in a small sample. And this is something that is in the appendix, and it's a small footnote here that you can read more about if you want. How large is large enough? We don't really know, which is why there could be substantial risk and problem with using this instrumental variable approach.
Right, and so in addition to this challenge of a finite sample bias and weak instruments I've just discussed, there's this other kind of shortcoming, which is not a bias or problem, inherent problem in specification, but a problem in interpretation rather, is the fact that with the two-stage least squared approach, the instrumental variable approach, we are not estimating the average treatment effect on everybody, on the whole sample. It's because this instrument kind of like extracts out and passes out the variation in our policy or treatment variable, and the variation we have left is for those who are actually changed or induced to change their behavior as a result of this instrument. And we're only looking at the treatment effect on that subset of the population, and that's why we're talking about the local average treatment effect. It's the impact on a subset of the whole population, and the impacts might be very different for those individuals or cities who are not affected by the instruments. And we'll get into this when we talk again about randomized control trials. It's within this context that this was developed, this intuition, but let's just talk through this quite quickly. As you remember, there's this distinction we have between the average treatment effect, which is a treatment effect on everybody in the sample, and the average treatment effect on the treated, which is the treatment effect on those who actually received the treatment, right? And we already kind of we're happy if we can estimate the average treatment effect on the treated for those who actually received the treatment. But when you use your instruments to like pass out this exogenous variation in your treatment variable X, you only examine the impact for the specific class of individuals for whom the endogenous X1 variable was influenced by the exogenous variable itself. And it seems a bit abstract, so I'm going to go through a more specific example, and hopefully this makes a bit more sense. And so let's say you want to look at the impact of going to a charter school on student learning. But of course, it's endogenous, which parents send their kids to a charter school or not. There could be positive selection bias, where the most kind of motivated parents send their kids to charter schools. And so looking at this relationship by itself would lead to a biased estimate. But what often happens in the United States is there's oversubscription. More people want to go to charter schools than there are spaces available, and there's some kind of public lottery. It's randomly assigned in literally this lottery, which determines who actually is able or allowed to go to the charter school or not. So in this case, you can use winning this lottery as an instrument for estimating the impact of actually going to a charter school or not. You can't use winning a lottery as a treatment itself, because as you will see, we don't have a perfect correspondence between winning the lottery and actually going to the charter school. There's some individuals who did not win the lottery and somehow go to the charter school. They were somehow able to cheat the system and get in. They're the always takers. They always go to take up the treatment. And there are those who do not go to the charter school even though they won the lottery. Maybe they just couldn't afford it, or a bunch of other stuff. They realize it's not their actual choice. And so winning a lottery is not the same as going to the charter school. We want to know what the impact is of going to the charter school, but that variable is endogenous, whereas winning a lottery is exogenous. And so we can use exactly the same approach. This is another example where we calculate the predicted value of X1, which is whether somebody goes to a charter school or not, based on, which is caused by the variation in Z, which is, again, you run this first stage regression, regressing whether somebody goes to a charter school or not on whether somebody won the lottery or not. But now this estimate, this predicted X1 actually has less variation. If you look at the data, it affects it. It only it has two values based on the average, based on whether somebody won the lottery or did not win the lottery, and it only looks at the variation, which is the increase due to individuals who took up the program, individuals who go to charter schools as a result of winning the lottery. So when you use this IV approach, when you calculate the treatment effect of going to a charter school, you're only looking at the estimated treatment effect on a subset of individuals who change their behavior as a result of the lottery. You're only looking at the impact on those who, as a result of winning the lottery, are now sending the kids to a charter school, and in absence of doing that would not have sent the kids to a charter school. We don't know what the impact is on the always takers, and we also don't know what the impact is on the never takers, those who never end up sending their kids to charter schools. Right, so just to conclude, the educated variable approach is incredibly powerful, incredibly smart design. It was incredibly, it was, especially in the past, commonly used by econometricians. There are unfortunately a lot of shortcomings and risks, so proceed with caution. And it has sort of fallen out of flavor unless it's used in very specific cases, when especially when it's used and combined with randomized controlled trials. The kind of most important concern about this is that we cannot test for this main condition of a valid instrument, which is this exclusion restriction and independence and monotonicity. So we don't, we have to assume that the instrument is exogenous, meaning that the exclusion restriction holds and its independence. The other issue is that if we have a little bit of a bias, it's not completely exogenous, a weak instrument could really inflate that. Then we also have this technical concern about a small sample bias. So, even though the probability limit converges towards the true population parameter, that only happens in very large samples. And so with smaller samples, we might always be in trouble. And then the other concern is that we only estimated the impact on a subset of individuals. It's those who are kind of the population that is kind of influenced by the instrument. And so our interpretation is also limited to those individuals. And I like the difference in difference. The difference in difference has kind of survived because there are ways to overcome this with instrumental variables. It's because it's very hard to test for this for these conditions. Often one has to tell a very compelling story and a narrative about why you think your instrument truly is exogenous or not. Right, that's it. Thank you very much.